Here's another example given a region, and notice that we have a function of y, not a function of x. So, when you see that, you're going to want to think in terms of summing horizontal rectangles bounded by these functions of y. So you're going to want to integrate with respect to y. So again, when you have a graph that's to the right of the other graph completely on your y interval, you want to subtract the smaller graph, the smaller function's values from the larger function values. So I would have the integral from -1 to 1 of e to the y, because that's the rightmost function, minus y squared minus 7, because that's the leftmost function. And notice on the interval -1 to 1, so that's marked by these two horizontal lines, e to the y is always greater than y squared minus 7. So I just have one definite integral. Here's another example where we're given the equations and we're supposed to sketch the region and determine which way to integrate to find the area. So remember that these are parabolas on their sides. You've got a function of y. So since your functions of y, you might want to consider integrating with respect to y, because then you're not going to have to change your functions and find the inverse and turn them into functions of x. But let's kind of explore that with this example. So if we integrate with respect to x, we have these vertical rectangles. And let's look at, so we would need to get these curves in terms of x, because the top of the rectangle is going to be coming from a function of x and the bottom of the rectangle is going to be coming from a function of x. So let's look at what we would have to do. So to turn these given equations into functions of x, we would need to find the inverses, or and solve for x. Solve for y. And so we would actually get four functions out of this. We would get the square root of x plus 1 would be the top half of that parabola that opens to the right, minus the square root of x plus 1 would be the bottom half of it, and then likewise for g of x, but we would have the square root of 1 minus x. So now we have four functions, and so if we used a vertical rectangle, we see that we're going to have two subregions. So one region is going to be from -1 to 0, and the top of the rectangle is going to come from the square root of x plus 1, and the bottom of the rectangle would come from minus the square root of x plus 1. And then on the region from 0 to 1, the top of the rectangle would come from the square root of 1 minus x, and the bottom of the rectangle would come from minus the square root of 1 minus x. So, but if we compare that to using y as our variable of integration, then our rectangle, everything becomes a bit easier, because now we just have one region, because x equals 1 minus y squared, this blue graph, lies entirely to the right of the red graph, which means that the x values returned from 1 minus y squared are always larger than the x values returned from y squared minus 1. So we just have one region, and we can integrate from -1 to 1 along the y-axis. And so we subtract the smaller valued function from the larger valued function. That's our integrand. Integrate with respect to y, and we get an area of 8/3. So in summary, finding the area between two curves comes down to knowing that you need to find where they intersect, if they intersect, so that those are the limits of integration, and remembering that you need to consider when the graph of one, where the graph of one lies above the graph of the other, because you might need to split the integral up into regions. And you can also integrate with respect to y, and remember in that case you have horizontal rectangles, and your integrand is going to be the function that's to the right of the other function. The function that's to the right is returning larger x values, so you subtract the other function from that.